Hey Chem 30s, we're going to look at part 3 of outcome 3 for equilibrium acids and bases, in which we're going to interpret some titration curves and identify buffering regions. So a graph showing the continuous change of pH during an acid-base titration, continued until the titrant is in great excess, is called pH curve, also called the titration curve for the reaction. So what we see in this image here is that we have, it says on top, we have acetic acid, CH3COOH, titrated with NaOH, which we know is a strong base. And what we see is that we had to have started out with the CH3COOH because our pH range starts out between 2 and 4, which means that we have a low pH, meaning very acidic. And what happens is that it is gradually, till we hit our equivalence point, that we see this big jump in pH. So the pH curve can help us determine a few important pieces of information. We can find our pH at the endpoint. This helps us pick an indicator for a titration, the pH of the initial sample, and volume of the titrant needed to reach the equivalence point. So endpoint refers to the point in a titration analysis where the addition of titrant is stopped. The endpoint is defined empirically by the observed color change of an indicator. So this one, really the big thing is an indicator saying that that is our equivalence endpoint. It just basically tells us, yeah, that's where we needed to. And usually what we'll do is we'll pick our indicator for somewhere in this range so that we know that we've gone past it. So pretty much here we have blue, and up here we have yellow. So one drop, it's kind of, looks a little bit maybe greenish. So one drop of solution, boom, yellow. All right. Endpoints are easily detectable because pH changes a great deal and very abruptly as the solution changes. Equivalence point refers to that point in any chemical reaction where chemically equivalent amounts of the reactants have been combined. So the equivalence point is essentially about moles is equal to moles. All right. The equivalence point is defined theoretically by the stoichiometric ratio from the reaction equation. There must be a strong acid or a strong base involved for the titration in order to get a noticeable endpoint. If you don't have a strong acid or a strong base, what happens is if you have a weak acid, weak base, all that's going to happen is that you're just kind of mixing solutions, and eventually it'll cross over, but it'll be a very slow. So we know that we have a strong acid, strong base. It's a very clear line like that. Weak acid, strong base, we're going to get something like this. When we have weak acid, weak base, we're really just getting something like this. All right. Oops. All right. Why for most of our titration does the pH hardly change at all? Take a moment. Let's just have you think on that a bit. So we have these two spots on here called buffering regions. And so we know about buffers is that they're kind of essentially what kind of stops us from getting this abrupt pH change. And then we also have the curve inflection point represents the reaction equivalence point. So this is our equivalence point here. And then right along that middle, the inflection point is right in that middle spot, which is our equivalence point. So at the equivalence point, the moles of acid equal the moles of base. So if we have 25 milliliters of OH minus at a concentration of 0.48 moles per liter, we have 12 millimoles. We have 24 milliliters of 0.5 moles per liter solution of hydronium. Then we also have 12 millimoles, and that's how we end up with our product of H2O. So choosing indicators for titrations, we have a few different solutions here, a few different indicators here we'd want to use, just depending on what works best for us. All right. An indicator is chosen so that pH range includes the equivalence point of a titration. That a pH curve is used to determine the equivalence point. So if we have a equivalence point we're looking at down here, we might use orange 4. If we have an equivalence point in the middle here, or about a pH of 7, we'd use bromoethanol blue. If we have a very high pH, we'd use alizarin yellow. pH curves with polyprotic acids or bases. Polyprotic acids can lose more than one proton, and polyprotic bases can gain more than one proton in Bronsted-Lowry transfers. If more than one proton transfer actually occurs in the course of a titration, chemists believe the process occurs at a series of single proton transfer reactions. So an example we have here is of HCl added to Na2CO3. So the first reaction that occurs is we have our HCl, which we know ionizes in water. So we're going to have our H0 plus, the Cl minus has dissociated. We have Na plus, CO3 2 minus, and H2O. What will react is we'll have our hydronium ion react with CO3 2 minus to produce water and HCO3 2 minus. Then after all the CO3 2 minus is used up, then HCO3 is the strongest base and it reacts with the HCl that is still being added. So if you continue adding this HCl, because when we add a little bit of HCl, we'll have this reaction proceed. As we add more HCl, we're going to have this reaction proceed, which is the HCO3 reacts here, and now it reacts again to produce water and H2CO3. So we're adding hydrogen to that base, and that's part of the Bronsted-Lowry theory, is why I can kind of explain this. So there are two quantitative reactions in this titration. So we got two endpoints on our pH. So we have an equivalence point here, and we have an equivalence point here. This is when we have HCl titrated with Na2CO3, which is what we just looked at. pH curve versus acid-base strength. Based on the strength of the acid and base reacting, we will see differences in our pH curves. So a strong monoprotic acid, we know monoprotic acid, if it's strong, is just one of those 6 strong acids, so something like HCl, titrated with a strong base. Our buffer regions are flat. The endpoint is always at a pH of 7. At the equivalence point, there's only H2O. All right. If we have an acid and a base, they neutralize. So we're going to end up with water, and then we'd also would end up with a salt. If we have a weak monoprotic acid titrated with a strong base, something like acetic acid being titrated with sodium hydroxide, we have a sharp change in pH at first and a pH at endpoint above 7. So what we see here is that our endpoint is actually somewhere, is going to be here. Our equivalence point is about there. And what we see is that that pH is about a pH of 9. Not a pH of 7, which we're used to with a strong acid, strong base. So this is the example I have. AOH minus reacts with CH3COH to produce the acetate ion and H2O. Again, we have this little jump here in pH, and then it kind of flattens out, and then our pH at endpoint is above 7. A weak polyprotic acid titrated with a strong base. What we have here is we have H3PO4 being reacted with sodium hydroxide. And the thing is that we know that we have monoprotic, which is 1. We have diprotic, which is 2. And we have triprotic, which we would also call polyprotic, which is 3. So HPO4, it will react as H3PO4, and then it can react as H2PO4. And then this will also react as well, but it does not want to react. It is such a weak acid. All right. So that's a weak polyprotic acid titrated with a strong base. Now we're going to work through one in which we have a weak monoprotic acid titrated with a strong, weak monoprotic base titrated with a strong acid. So what we're going to have is we're going to kind of have a little jump in pH off the get-go, kind of flatten out, and then it'll drop, and then go something like that. All right. One mistake I did make is that this should probably go more like this, and then it'll drop down, like so. We have a weak polyprotic base titrated with a strong acid, which we have, that's sodium phosphate titrated with HCl. And again, we go down here, we have 1 equivalence point and 2 equivalence points. So in summary, we have some titration generalizations in which strong acid, strong base reactions are quantitative 100% and have an equivalence point of pH of 7. Strong acid, weak base quantitative reaction equivalence points have a pH below 7. Weak acid, strong base quantitative reaction equivalence points have a pH of greater than 7. And polyprotic entity samples produce sequential reactions in titration, each of which may or may not be quantitative. Essentially, the biggest thing is with this stuff is just making sure to take your time and do some practice questions with it, because the biggest, especially for anything in chemistry, is make sure that you have that practice. If you haven't practiced it, it is very tough. If you put in the work, you do some practice, which you have here. One page, you're going to write down what sort of things we have reacting here, and then you have a couple practice questions. I will put the keys up for those. And that concludes our lessons for equilibrium, acids, and bases. Make sure you ask questions for me. Always glad to help. Just shoot me a quick message on Google Hangouts if you want to actually sit down and go over something. I'm more than happy to schedule a Google Meet, and we can work through some questions that you may have. All right, take care. Have a good one. We'll talk to you later.